All right, so remember for a power series, right? For a power series, we have given a power series, actually get a function, and conversely, a function, nice function can be expressed by power series. That will be next topic. So given given power series. Okay. If we know the convergence of radius convergence, then we get a function define that function, right? So let denote the radius of convergence. Okay, and of course we assume I is positive. Okay, then we get a function on the interval a minus r, a plus r. Okay, so that function, of course, is defined by the function is given by this. I call it generalized polynomial. It's polynomial degree. The polynomial degree infinity. Okay, so we get a function, and then and then so every power series defines a function. Okay, let's look at the following example. It's our favorite example. We consider this power series just x to the power n. Okay, and we find out. We find out this one is convergent. Okay, if and only if absolute x is less than 1. So this is convergent. Actually, is absolute convergent if and only if the absolute value x is less than 1. Okay, so we get a function. So then we get the function f of x on the interval from -1 to +1, right? And a surprise to me, this function is nothing but 1 over 1 minus x. In fact, okay, this is going to be just 1 over 1 minus x. So we remember, this is going to be k, n start from 0, x to the n, right? This is going to be 1 minus x to the k plus 1, 1 minus x to the k. So you letting k goes to infinity, right? What do you get? Left-hand side is x to the n. The right-hand side is just 1 over 1 minus x, because if absolute x is less than 1, and that limit is going to be 0. Okay, so that is why. So f of x is nothing but is a one function we are familiar with that. Okay. Now, of course, we have to solve an inverse problem, like for what function you can find the power series representation, right? Okay, so here's a definition. Power series, so-called power series representation. Given function f of x, okay, on some interval a minus r, a plus r, if f of x is expressed in the form Cn x minus a to the power n. Okay, and this is a convergent on the interval then this power series is called the power series representation of the function over the interval. Okay, called because that's a unique one, power series representation of f on the interval a minus capital, a plus capital. Okay, so that's the converse. You know, you get your given function. You want to find the power series representation. So in other words, 1 over 1 minus x. Okay, the power series of representation 1 over 1 minus x at the origin is going to be nearby the origin is going to be sigma of xn. Okay, so by above argument, okay, the power series yeah, above let's say, so the power, yeah, we can also say this is a power series. It's called the power series representation of f over the interval, or sometimes you can just say, or at x equals 8, because you know sometimes you don't want to specify the radius. Okay, then just say at 8. Okay, so let's look at the example. F of x equals 1 over 1 minus x, right? Right, now this function is defined for all x, right, except for 1. Right, so actually the function, if you draw the schedules graph, and this is x equals 1. When x is greater than 1, 1 minus x is negative, so it's below the x-axis. When x is less than 1, it's going to be like that. When x equals 0, this is a 1. So this is a graph, right? Around its origin, I can find a power series representation, because this is a 1, so the largest possible interval around 0 is going to be from -1 to +1, right? So we know that, okay, we know that f of x equals xn for x less than 1. So this is a power series of the function. But that only covers that area, right? You will say that, how about something else, right? Away from that point, right? What you can say? Like, can I express a power series find the power series representation for the function, at least around that point, okay? I can do that, okay? For any, it is a power series representation at a equals 0, okay? Around this origin, okay? With the radius I equals 1. Okay, I should say that more precise here. So for now, let's look at for A, not equal to 1, arbitrary point A. Can I find the power series representation over the interval around A? But the interval will not include 1. I can do that for any A not equal to 1. Let me show you how to do it. Okay. So f of x, still f of x, is 1 over 1 minus x, right? No problem. So I'm going to write the x and let u to be x minus a because I want to expand in u, right? Okay. So then x is going to be u plus a. Okay. X is going to be u plus a. Okay. When x, yeah. So then this is going to be 1 minus a minus u. Okay. So a is now going to be 1. So I'm going to take an a out. This is very useful technique. So I take 1 over a out. What you get is going to be u over 1 minus a. Okay? So as long as u over 1 minus a is smaller than 1, I can expand it. Okay? I can expand it in the form u over 1 minus a to the power n, as long as absolute of u over 1 minus a is less than 1, right? As long as this piece is smaller than 1. Then, what do you get? You will get okay, and here u is less than 1 minus a. All right, so let me rewrite this again. And the u is x minus a to the power n. And x minus a is less than 1 minus a. Yeah, it's less than r. Let's say r is going to be absolute value 1 minus a. Okay. All right, so that's it. So this is a power series representation for, yeah, so it is the power series representation of the function of f around at a, okay, with radius going to be absolute value 1 minus a. Now what does that mean, absolute 1 minus a? It cannot larger than that. The point is, if you look at the picture, yes, this is a 1, right? And arbitrary point a here, right? So this is the largest r you can get, okay? And then this is going to be absolute value 1 minus a, okay? Yeah, the difference between 1 and a, okay? So over that interval, I can have a power series. Okay, that power series is equal to the function. In other words, yeah, let me, okay. In other words, this one is going to be an x minus a to the power n, okay? And this is holds when a is less than equal to r and I is given over that. All right, so this function is good. Yeah. Right, so I can actually find the power series representation for this 1 over 1 minus x everywhere, except for 1, because the function is not defined 1. But the interval, you know, the power series must be say here on which interval, right? These two functions match. Power series defined function, and function itself is there already. So they match only on the largest possible interval is, you know, the interval touches the vertical asymptote, vertical asymptote. Okay, this is largest interval you can get. All right, but this is just 1 over 1 minus x. How about other functions, right? Are we able to find other functions? This still will be next topic, but right now let's understand the power series representation first. All right, so the important theorem says that in this important theorem is, yeah, we use this theorem, we can find a power series representation for the other functions. It says that okay, so we assume that, let me state this slightly different. Assume that a function f is going to be this. Okay, and this holds over that here, okay, where I is the radius of convergence. Now, okay, of the power series. Because the formula for f could be like 1 of x, can be defined on more on x outside this interval. I don't care. I just say there's a function f. If it can be expressed as a power series over that interval, okay, then we can have the following property. Okay, then the function is differentiable. Then the derivative of the function can be also expressed by this integral, by this power series. In other words, you can differentiate. Yeah, if you want to differentiate the function, you just differentiate the corresponding power series, term by term, add them together. Okay. Not only that, and this holds for x minus a still less than r. Okay. Moreover, the power series, the radius convergence of this new series is still same. Okay. R is still the radius of the convergence of the power series in this radius convergence of this power series. Okay. It doesn't matter. The radius convergence does not change if you put the n in front of each term. Right. So that's good. So first of all, the function is differentiable. Second, if you differentiate each term in the power series, you get a new power series. But the new power series, the radius convergence is still the same. Okay, that says that. Okay, and then they match. Perfect. So if the function has a power series representation over some interval, then no matter how many times you differentiate, you can easily get the power series representation for the derivatives, and they always match. And they don't, the radius of convergence do not change every time when you differentiate the power series. Second, the integral of the function, right? It's still the same as you just evaluate the integral of each term, okay? And I think when c equals n plus another constant, yes. Okay. And this holds for absolute x is less than now, okay? Not only that, r is still the radius of convergence. Okay, so the radius convergence of this series, of this power series, is the same. So you see, every time you divide by n plus 1, and you essentially do not change the radius convergence, okay? So it's the same. So that's good. So now let's go back to the following problem. let's go back to 1 over 1 minus x equals, I know we have this, right? The radius of the convergence is going to be what? We have this identity. So I'm going to differentiate. How about that, right? Let's differentiate. If I differentiate, this is going to be, if we differentiate, it's a square, right? Yeah, you get 1 over square positive sign. So you have nx to the n minus 1, and this still holds for this. So you have this. So you get power series representation for 1 over 1 minus x squared. Right? And you can keep it going. Right? You can differentiate again. Now you can also change the sign. Yeah, let's change the sign. So if you replace x by negative x, you can, yeah, this is by the theorem, by the above theorem. Right. How about integrate? Right? And the plus constant. Right? You also have this. The integral of 1 over 1 minus x, that is going to be natural log 1 minus x. Okay? Okay? When you differentiate, you get negative sign. So it's going to be, you're going to be this. Okay? And the plus constant. Let's figure out what is constant. So if x equal to 0, the both sides is going to be 0, right? So let x to be 0. You get natural log of 1 minus 0, which is 0, and 0 plus c. So c must be 0. This implies c 0. So finally, I got the following. Finally, we got this power series representation. Okay. See, I create some, right, based on the original. So this holds for x less than 1, okay? The radius of convergence on the right side is always 1. The radius of convergence is not changed, okay? If we integrate each term, it's not going to be changed. And then they match. And then the function on the left-hand side is the natural log 1 minus x. This is only defined for x. Now this time, the x is, this is only defined for x less than 1, okay? It's not going to be, this is defined for x less than 1. And 1 over 1 minus x, this function is defined for x not equal to 1, okay? So this, but for this function itself, it is defined for, is for x greater than 0 or x is less than 1. Cannot be defined for positive x, okay? It's okay. So we get, yeah. So for the natural log of function, okay? For the natural log of function, this is x-axis, this is y-axis. How do you draw the graph? It's only defined, yeah, let's draw the graph for natural log of 1, right? When x equals 0, it is 0, right? When x is kind of close to 1, it's going to be negative. I think that's the picture. Right? This is a y equals natural log of 1 minus x. Yeah, what we did here is we find the power series representation for the function around its origin. right? So we know that, yeah, this is a holds over that interval. Then you say, then how about somewhere else? For any number which is less than 1, can I find a power series representation around the A if A is less than 1? The answer is yes. Okay, how to do that? Okay, here's the question. Okay, find the power series representation for the function f of x equals natural log 1 minus x. Okay, at a should be less than 1 clearly because the function is not defined for a greater than 1, right? So whenever a you choose, the interval is already determined. I can tell you before that. Okay, this is a picture. So if a is here, then this is the interval you're going to get. The radius r is going to be 1 minus a, right? So it's picked. So let's find the formula for that, right? So this formula must be in the form like a Cn x minus a to the power n. Okay? So let's determine the coefficients of Cn. So this will be useful. Yeah, so let's see. Okay, so I'm going to let u to be x minus a, right? Okay, good. Then x is going to be u plus a. So f of x, which is natural log 1 minus x, is going to be natural log 1 minus u plus a. Okay? So that would be natural log 1 minus a minus u. Then what? I'm going to use the already known result, which is this one. Okay? Okay, x should be less than 1, right? 1 minus x. How can I do that? I take 1 minus a out. So I get 1 minus u over 1 minus a. So I separate. Okay. Now, this is a constant. Don't worry about that. What we needed to know is this one. This is some x, right? So according to above formula, it's going to be negative n start from 0, 1 over n plus 1, and the x, right? That's u over 1 minus a to the power n plus 1. Okay, and this holds for u over 1 minus a less than 1. Okay. Yeah, what I did here is just applying the above formula. View this part as inside circle as a 1x. Look at this. Look at this. We already know this result, right? 1 minus x is going to be that. Absolute x should be less than 1. Okay. So let's rewrite this again. It's natural log 1 minus a. And I'm going to take 1 minus a out. And the u to the 1 minus a is x minus a to the power n plus 1. Okay? And this is true when u is less than, and u is going to be actually is x minus a. So this is true, x minus a is less than 1 minus a. Okay, this is my r. Okay, I already show you. All right, so we find the power series representation for the function at any arbitrary point. Okay, so when you can change it to use a new index. So if you don't like n plus 1 here, you let k start from 1. What is k? K is the n plus 1. It's so it's going to be k times 1 minus a to power k, right? and x minus a to the power k. Okay, k is going to be n plus 1. And this holds for x absolute x less than 1, less than r. Okay, so we get this formula. Now, there are some other formulas you don't need to, yeah, we just modified. You don't need to use that theorem, okay? For example, find the power series representation for the function f of x equals natural log of 1 plus x, okay? At a equals 0 at its origin. If you're not told that this is power series around this origin, then it's not clearly given. Then just find the power series around the origin. Okay. Now here's the 1 plus x. How to do that? We know the power series representation, right? This is we already know that 1 minus x is going to be negative. Right? Absolute x is less than 1, right? We know that. How can I get the power series representation for the given function, natural log of 1 plus x? All I have to do is just replace x by negative x. Okay? You let u to be negative x, right? Right? That's what you want. So then x will be negative u. Oops, where is my function? Okay. So let u to be 1 of x. Then natural log of 1 plus x is going to be natural log of 1 minus u, right? Yeah. Then, according to the above formula, you have no, just the positive sign. Okay. So the absolute value is less than 1. That holds. Now what is u? You replace u by negative x to the power n plus 1. And the absolute value u is the same as absolute value x. Done. We're done. Okay. You can modify this a little bit. So you get negative 1 to the n plus 1. You get alternating series, right? And the n plus 1 has another one n here. And this is a fine answer. Okay. Now, if you don't like n plus 1, you can change it to k equals 1, negative 1 to the k minus 1, k, x to the power k. Right, so there's no first term there, 0 term, constant term, no. Just begin with x, right? So it's going to be, when k equals 1, it's going to be x of 1 minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. And that holds for, this is a holds for x less than 1. So the natural log of 1 plus x is almost like that. It's almost, right? And I think if x is close to 0, then the first few terms already very is good approximation of natural log 1 plus x. Right? The rest of the terms can be ignored if x is close to 0. Right? So how about find a power series representation for the function f of x equals 1 over 1 plus x squared. Whoa. Yeah, think about this. When I say power series, it's not specified at which point you have much freedom, but usually means the power series at the origin, okay? Because the function is defined at origin. Okay, you can, yeah, I think in the book that says that this is what that means. Okay. Otherwise, it's unique, right? That just find the power series representation. That's my understanding. So that means you still have freedom, you know, power series representation is not clearly defined. You have to usually have to mention at which point, nearby which point, okay? So like example 2, say find a power series representation for the function 1 over x plus 2. Now this is actually he find out a power series representation at 0 as the origin. Okay? So find the power series representation. How do you do that, right? This is very similar to the 1 over minus x. So it's 1 minus x. I know, just recall that formula, right? Right. Now, what are you going to do? You all you have to do is you let, you know, this can be, I can change the variable, right? No problem, right? Yeah, just change the variable, no problem. Then I let u to be negative x squared, right? No problem. All right, then what I get? It's going to be 1 plus x squared equals and u is negative x squared to the power n, and absolute of a negative x squared less than 1 here. All right, so you can rewrite this, you can get alternating series. Right? And negative absolute of x squared less than 1, it's the same as this one. Right? But it's very difficult to find the power series of this representation for this function somewhere else. Okay, for example at 10, okay, because it's not a, yeah, you have to use a so-called Taylor series to find out. All right, let's do more exercise. Yeah, this is number 8. So the function here is going to be x over 2x squared plus 1. Find the power series representation for this function. Okay. How can I do that? Wow. There are a couple ways to do maybe. Oh, I'm not. Let me finish this other problem first. So look at the above identity, right? This holds for x less absolute x less than 1. So I can integrate, just realize that, right? If I integrate according to the theorem, you will get integrate each term, 2n plus 1 x to the 2n plus 1, right? And plus constant. And this should be still hold for x less than 1. What is the integral of 1 over 1 plus x? Arctangent x. Arctangent x. So you will get the power series representation for the arctangent x. That's cool, right? And the c must be 0. Yeah, you can check that. C must be 0. C must be 0. Right? Because the arctangent is 0 is 0. And the other side, all the terms will be 0 when you plug a 0 for x. So you cannot use integrals or derivatives to find the power series representation for more general functions. Not all of them. Okay. So let's go back to the problem number 8. Okay. Step 1. I can find the power series representation for this function, which is going to be, right? And which is going to be, let's do it directly. I'm going to do this. Okay. And this is this is a u, right? Okay, so 1 over 1 minus u. So according to the known formula, okay, it is going to be u to the power n. So negative 2x squared to the power n. Okay. And this holds for negative 2x squared less than 1. Okay, let's rewrite this again. Okay, and here, how can I express it? I think I'm going to, it's less than 1 over square root 2. Okay, or square root 2 over 2. So that's the radius convergence. But I have x on the top, right? Let's just multiply it. So x over 1 minus 2x squared is going to be just multiply x to 2n plus x, that's a to 1. That's it. Then you still have the same radius convergence. So we solve the problem. Okay, just modify the function and use the given formula. We only use a single formula over and over again right now. Okay. Yeah, for practice, let's do the problem number 15. Natural log of 3 minus x. Okay. Find a power series representation at the origin. Okay. At A equals 0, okay? So how do you do that? Well, first of all, you record the formula we already got, right? The two formulas. The one is nature log 1 plus x. The other one is nature log 1 minus x. Nature log 1 minus x, okay, is going to be, right? So record that nature log 1 minus x is negative. I think it's going to be 1 over right? We do that. Right, so we already, it's just integrate on both sides. Yes. So if you forget that, you just integrate 1 over 1 minus x on both sides. Right. So this is a holds for x less than 1. We have to use this product. How about nature log of 3 minus x? You have to change 3 to 1. Right? So that is going to be nature log of 3, 1 minus x over 3. So it's going to be nature of 3 plus nature log of 1 minus x over 3. Okay? Then you apply, nature of 3 is just a constant. The second part is negative and n plus 1 here, and x over 3 to the n plus 1. Take the constant out, and here just x to the power n plus 1. So this is a power series representation, and I know where it is hold. I think when absolute x over 3 is less than 1. So in other words, x is less than 3. Okay, this is a radius of convergence. Okay, if you just look at the power series, and you can determine the value of x for which this power series is convergent using the ratio test or row test. Okay. So today we just learned the power series representation. What is power series representation? And also we learned that if the function can be expressed as a power series, then you can, both sides can differentiate, can integrate. You're not going to change the convergence of the radius on the right-hand side, but the function will be changed, okay? For example, 1 over 1 minus x is defined for all x not equal to 1, but the integral will be nature log of 1 nature log of 1 minus x, which cannot be defined for all x, okay? But then on the same interval we are talking about, you know, for the power series, those two functions still match, okay? Then we differentiate those formulas, identities, and we get power series representation for more general function, even including arctangent x, right? And a typical problem like this one, you know, you're given nature log, but it's not in the form 1 minus x. You have to modify it to the nature of 1 minus x. Then you can use that formula to find the power series representation. All right, so today we're going to take a quiz. I hope everybody's here.
The lights. Yeah, please. Can see.